Another fascinating industrial application of electrochemistry is the electrolysis of brine or sodium chloride solution. It uses huge amounts of electricity, but it produces three really important products: chlorine, hydrogen, and sodium hydroxide. Right, let's consider the chemistry involved in the electrolysis of brine in the chlor-alkali industry. Firstly, a reminder that brine is the name that we give to a concentrated solution of sodium chloride. So if we consider a solution of sodium chloride, obviously we have Na plus sodium ions and Cl minus chloride ions. Remember that those ions are obviously dissolved in water, and so we have water molecules present as well. If we put in the electrodes, the positive and negative electrodes, we're going to look at what happens individually at each of those electrodes. Let's start at the anode. That's the positive electrode, the electrode at which oxidation takes place. So the ions that we have in solution are the Cl minus ions that will be attracted to the positive electrode, and the half reaction there is relatively easy. The Cl minus ions will lose electrons. There's your oxidation reaction that takes place at the anode, and it will form chlorine gas, Cl2. And so chlorine will be formed at the positive electrode. If we then have a look at the cathode, the negative electrode, the Na plus ions are obviously attracted to that negative electrode. But remember, we also have water molecules present. And the question we need to answer quickly is which of those will be discharged preferentially. If we have a look at table 4b, we can see that it's actually very, very hard to electrolyze sodium ions to sodium. Its E naught value is minus 2.71. And I think you might appreciate that sodium is very reactive when it forms sodium ions, and therefore to try to get the reverse reaction to take place, to add any electron to a sodium ion, is very, very difficult. And so what happens is that the water molecules are electrolyzed preferentially. They are reduced, so water molecules gain 2 electrons, and they form hydrogen gas and hydroxide ions, H2 and OH minus ions. And so in our solution then, in the cathode department, we have unreacted Na plus ions, and we have OH minus ions that have been created from the reduction of water. And I hope you know that those two together give us sodium hydroxide. But there's a problem. At the positive electrode we have chlorine gas. At the negative electrode we're forming hydrogen gas. And you may well know that those two are explosive together with heat or light. And so the design of the cell has to take this potential problem into account. This is what the membrane cell looks like. Notice that the two compartments, the anode and the cathode side, are separated to try and keep the products away from each other. The anode compartment is connected to the positive, and so that's a positive electrode. Cathode is negative. If you now focus down bottom left, where it says saturated brine, that's where our aqueous sodium chloride is introduced into the anode compartment. The chloride ions are then attracted to the positive anode, and they are discharged as chlorine gas. Now the line down the middle represents what we call a semi-permeable membrane. It's a polymer substance, and it's designed in such a way as to allow only positive ions to flow through it. And so the Na plus ions that are in the anode compartment can flow through to the cathode, but the Cl minus ions can't. Now the water molecules in the cathode department react on the negative cathode, and they discharge hydrogen, and if you remember, they also form OH minus ions. And so in the cathode department we're forming hydrogen gas. We've got the Na plus ions who have moved through the semi-permeable membrane, and together with the OH minus ions form sodium hydroxide. So there are 3 products then: chlorine from the anode, hydrogen from the cathode, and sodium hydroxide also from the cathode.